Hi, this is Professor Fernandez, and in this video we are going to talk about Module 3 of Lesson 10. So the topic here is properties of double and triple integrals. And these properties, there are many of them, and I've listed the most important ones over here. Just want to make a few comments before making a few other comments about these properties. The first comment I want to make is that you'll notice that there's a lot of R's and B's here. So I'm trying to stick to the notation that we've been using in this lesson to denote a rectangular region, that's the R, and then a rectanguloid region, that's the B, when we're talking about a triple integral. However, these properties hold not just for those type of regions, they hold for more general regions. We'll talk about those more general regions in the next lesson, but this is a way for me to economize and not have to go back then and give you this entire list again for all of those more general regions. The second thing I want to mention is that these properties all relate one type of integral to other types of integrals. So we're going to assume implicitly that every integral on each side of the equation for each property exists. Meaning, for example, this is a number, or this integral exists. It's some number we can calculate. Same thing with that one, and same thing with that one. And then the property itself tells us then that they are equal in this sense. One is the sum of the other two. Okay, so to go through these properties here, the first two properties are just telling us that the integral of a sum is the sum of the integrals, in whether we're doing double integrals or triple integrals. The next two say that the integral of a number times a function is that number times the integral of the function, whether doing double or triple integrals. And then over here we get to something that looks a little different, even in the way that the property is stated. These are the generalizations of this property of integration that we know from single variable calculus, where we can split up the domain of integration. Let's say here we're thinking about integrating a function from a to b, or sorry, a to c, and then we just kind of pick a point somewhere in between. You know, it actually doesn't have to be in between. That's one of the things you likely learned. But just for illustrative purposes here, let's pick it to be in between. Then we can split up the integral from a to c to be the integral from a to b plus the integral from b to c. So that's what we're doing here in these properties. If we're talking about double integrals, we can imagine our region being split into two non-overlapping regions, R1 and R2. And then the integral over the whole thing is the sum of the integral over its pieces. So for example, if this is our region here, this is R, we're integrating over this whole rectangle, we might decide to chop up the rectangle into this R1 and then this R2. For the purposes of this property, we want these regions to be, they compose the original region. In other words, that you have taken the full region and then chopped them up into these subregions. And we also want them to be non-overlapping, so that we don't double count some volume, basically. And then this property says that the integral over the whole thing is the sum of the integral over its pieces. Similar thing for the space version of this, when B is a domain in space, for example, one of these box domains. If we split it up into two other boxes, maybe this red one over here and this blue one over here, similar thing, excuse me, the triple integral over the red box plus the triple integral over the blue box is the triple integral over the whole box, because they are split evenly, so to speak, and they are not overlapping. Okay, so the last two properties are also ones that you know from single variable calculus, just expressed differently in this multivariable context. The first one says, if I find the double integral of 1 over a region R, I get the area of R. So this is certainly a property that generalizes. This is not just about property for R being a rectangular region. And just to draw this out, even though we won't talk about non-rectangular regions until the next lesson, what is really going on here? Well, the function f here is 1, z equals 1. So we're looking at z equals 1 as the function, which is just this plane. And then whatever the region R is, we're thinking of that as a region in the xy plane, that's R. You can think of this in two ways. We're finding the volume of this solid which has area R. So the volume is the area of R. It's all of this multiplied by the height of this, cylinder that we've created, this solid cylinder. And that height is just 1, because remember, we are on the function z equals 1. So you can see that in this case, the volume is 1 times the area of R, which is equal to the area of R. And it doesn't matter whether R is rectangular, doesn't matter what shape R has. So that's just a very quick, intuitive way to understand why this volume integral, a double integral that produces a volume, produces an area of a region. A very similar thing happens here with the triple integral. So integrating the function 1, which I cannot plot for you because this is w equals 1. W is what we call f of x, y, z. So to plot this function, I would need, again, an axis for this, and then 3 axes for these. I need to be in 4-dimensional space, which I have no idea how to plot for you, and I think very few people, if any, can actually do that. So I can't visualize this for you, but I tell you that the same mathematical result holds. If you are integrating, triple integral, the function 1 over some rectangular or non-rectangular region in space that is a solid region, could be a sphere, solid sphere, could be one of these box domains, you end up getting the volume of this region. All right, so those are all the properties that, that I at least would like to show you. And you can see here that there were some typos. This had a V in it, so I will fix that so that it matches with this B. And now what I want to do is work through some examples to show you how these properties come in handy in calculations of integrals. I'll also show you one little trick for calculating integrals in very special cases, double integrals, or even triple integrals. Okay, so the first thing we're going to do is work on this example. So this is a double integral of a sum of 2 functions over a rectangular region. So we are going to use one of the properties here to split it up into the double integral over r of x, y, plus the double integral over r of x squared dA. All right. And here come a few other kind of like tips and tricks to speed things up. The first interesting one is that when I look at a function like an integrand, like x, y, and I forgot my dA, so I'll put it in there just to be mathematically proper. When I look at a function, this integrand here, x, y, which is a product of only a function of x with only a function of y. Actually, when you think about what I'm integrating, for example, if I did integration in x first, the y is a multiplicative constant for the purposes of integrating with respect to x. So it just kind of goes along for the ride as a multiple. And then I'll be left with a single integral in terms of y. So I could think of it as really separately integrating x with respect to x and then separately integrating y with respect to y, and then multiplying the two. So this is one of the nice little tricks. And it's not really a trick, it's a property, but it's not one of the properties listed above here. But it feels like a trick because it's multiplying single integrals versus doing a double integral. But it's really because the integrand itself has this very special structure, a product of only a function of x with only a function of y. And if we do that, then the integral here is from 0 to 1 in x, from -1 to 1 in y. And this integral, this yields x squared over 2, evaluated from 0 to 1. That gives me 1/2. And this yields y squared over 2, evaluated from -1 to 1. I get 1/2 minus 1/2, so I get 0. Okay, so that's going to multiply out to 0. Over here, a different trick, a technique that I want to show you. So this is integral from 0 to 1 times integral from -1 to 1, or I wouldn't say times, but dx, or sorry, here the way I've written it, it's actually dy dx. Okay, so this is actually part of the technique. So this first integral, I'm integrating with respect to y, does not have any y's in it. So I can easily switch the order of integration here and also do the product thing that I did over here, because this is a function of x times a quote function of y. The function of y is the number 1 that is hidden in here. I could do that, but to show you this other technique, the fact that there's no y in this integrand tells me that whatever I'm integrating over in terms of y is just going to yield a number. It's literally as if I was integrating this. So I integrate that and I just get 1 minus -1, I get 2. So I'm going to go back here and then say that this integral equals 2 times the integral from 0 to 1 of x squared dx. Okay, so that's a little technique that, over time will speed up calculations. And then here I get 2x cubed over 3 evaluated from 0 to 1, which gives me 2/3. Okay, so I have calculated these integrals separately, and my property of integrations, the first one we talked about, tells me that this whole integral is the sum of these other two. So then my final answer is this plus this, so just 2/3. Okay. And here again, I can try to visualize this and plot this and think of this as a net sign volume. I won't do that in this video. We've done enough of that in the previous videos in this lesson. Here I really just want to focus on helping you maneuver around and use different properties and techniques to calculate integrals. Okay, so now I'm going to go over to this part B of the question. This is now a triple integral of this function over this domain. And I'm going to use a little bit of what we were just talking about. So first thing I'm going to do is split this up into the triple integral of x squared plus triple integral of y squared plus triple integral of z squared dv. I put dz there because my brain is anticipating the next thing I want to say, which is, in this first one, there is no y, there is no z. So I can do exactly the same technique that I did over here. So if I integrate the function dy, it's not the function, but if I write out the integral dy from -1 to 1, this again gives me 2. And if I write out the integral from 1 to 2 of dz, this gives me 2 minus 1, which is just 1. So this integral over here is this number 2 times this number 1. It's 2 integral of x squared dx. And the x goes from 0 to 1. Plus, I can do the same thing over here, but things change a little bit. So over here, there is a y that I'm going to end up integrating. So I'm not integrating dy, I'm integrating y squared dy. So I'm not going to end up with a 2. However, over the x interval, I am going to integrate for this integral dx. So that'll be integral 0 to 1 dx, which just gives me 1. So this here is a 1 times, because there's no z, the z portion of this triple integral is the same one over here. So another 1 times a 1. And then the y portion is left. So now it really is y squared dy from -1 to 1. And then for the last integral here, the x1 gives me 1, the y1 gives me 2, and then I'm left with the z1, which is from 1 to 2 of z squared dz. Okay. So again, these are all intended to be tips, techniques, strategies to reduce double, triple integrals to simpler integrals to solve, or to break them up to make them simpler. And there are certainly many other ways we could do this problem. But these are good things to keep in mind for the practice problems that are suggested later on in the lesson notes. So we keep going here. We now have 3 single variable integrals that we're just going to put together. The first one gives me x cubed over 3 from 0 to 1. The next one gives me y cubed over 3 from 0 to 1. And the last one is 2z cubed over 3 from 1 to 2. And I noticed here that the y goes from -1 to 1. And then I just work this out. So this is 2 times 1/3 plus, over here I get 1/3 minus -1/3. So I get 2/3 again. And then over here I get 2 times 2 to the third over 3 minus 1 to the third over 3. And then I get 2/3 plus 2/3 plus 7 over 3 times 2, 14 over 3. And that gives me 18 over 3, which is a nice solid quote unquote 6. Great. So these have been just some quick illustrations of properties of integrals. We talked about many of these, so not all of them. And then I also added some of them over here for you to consider. This particular property where you have the integrand being a function of only x times a function of only y, or even in the 3-variable case, you add times a function of only z. In those cases, you can split up the integral into products of integrals of each one of the respective functions. And that's a very useful property. You'll see that come up in some of the solutions I write to the practice problems later on. Great, so there's not much else to go over in this video, so I will see you then in the next lesson.